So now our next speaker is Eleni-Alexandra Kontou. Eleni, can you please share your screen?
Yes.
Are you there? Okay.
I'm here.
Okay.
Can you see my screen?
Yes, yes.
Yes, we can. Yeah.
Okay, so yes, I'm just to introduce our next speaker is Eleni-Alexandra Kontou. So the title of the talk is on semiclassical singularity theorem. So your talk will be 25 plus 5 minutes. So please start.
Thank you. I would like to thank the organizers for inviting me to speak in this conference. So in this talk, I want to summarize some recent work on the progress on semiclassical singularity theorems that I did with my collaborators. And it's mostly based on 3 papers from the last year and a half that have appeared on arXiv. So I will start with a little bit of background on singularity theorems. So first of all, the definition of a singularity in the context of singularity theorems is that of geodesic incompleteness. So in that definition, space-time is singular if it has at least one incomplete geodesic. So the disadvantage of this general definition is that we don't know here if the singularity is, for example, a curvature singularity, so the type of the singularity that we have. But it is a pretty powerful definition because it allows us to prove it pretty easily. So let's see the singularity theorem structure. There are 3 basic conditions in singularity theorems. Here I will remind you the conditions for the classical singularity theorems of Hawking and Penrose. So first we have the initial or boundary condition. In the case of the null geodesic, this is the existence of a trapped surface. A trapped surface is a codimension 2 hypersurface that has 2 null normals with negative expansion. To understand that, we can see the case of a Schwarzschild geometry. So here is a plot in Eddington-Finkelstein coordinates of the 2 sets of null arrays that we have in Schwarzschild. So the dotted line is the horizon or the trapped surface, which coincides in this classical geometry. And we see that both sets of null arrays actually inside the horizon are going towards the singularity. This is pretty unexpected. It's like shining a flashlight outside of a black hole, but then the light goes back inside. So this is the trapped surface in this case. In the case of the time-like geodesic, we have a spatial slice with negative expansion. And this is, for example, what happens in our universe. So we have the spatial slices in our universe in an FRW universe. And if we look back in time now, we see that the expansion of these slices is negative due to the expansion of the universe, of course. The second condition, which is the one I'm more interested in this talk, is the energy condition. Energy conditions are restrictions of the stress energy tensor, and they consider to express physical properties of matter. This is in quotes because they don't always express properties of actual matter. For null geodesic, we have the null energy condition, and for time-like geodesics, we have the strong energy condition. So these are the 2 conditions. The null energy conditions is the stress energy tensor contracted with 2 null vectors is everywhere non-negative. The geometric form comes from applying the Einstein's equation, and it's the Ricci tensor contracted with 2 null vectors. We can understand the meaning of the null energy condition if we use a perfect fluid stress energy tensor, and there the null energy condition is telling us that the energy density and the pressure are everywhere non-negative. The strong energy condition has a little more complicated form in its physical form with the stress energy tensor, but the geometric form is very similar with the null energy condition. It's the Ricci tensor contracted with 2 time-like vectors here. It's also a little harder to understand the interpretation of the strong energy condition. Why does the n-3, n is the space-time dimension of rho plus n-1p non-negative? It's not as clear as the null energy condition. And in fact, the strong energy condition is actually violated even by some classical fields. But I'll say more about that a little later. The third condition is the causality condition. And this is the existence of a Cauchy surface, which is space-like hypersurface which intersects causal geodesics only once. I'm not gonna talk about the proof of the singularity theorems in this talk. I'm just gonna very schematically talk about the proof structure. The initial condition is telling us that the geodesics start focusing. The energy condition guarantees that the focusing of the geodesics continues. And then the causality condition implies the non-existence of focal points. So the contradiction between the first two conditions and the causality condition leads to the conclusion, which is geodesic incompleteness. Since the first two say that there are focal points, the third one is saying that there can't be, then the geodesic must end. So we have a singularity. Now, what do we need to go from classical to semi-classical singularity theorems? Unfortunately, we cannot apply immediately the classical singularity theorems to semi-classical gravity. And the main reason is the point-wise energy condition in their assumption. So these two conditions that I presented, the strong energy condition and the null energy condition, are violated by some classical, especially the strong energy condition, and more importantly, they're violated by all quantum fields. So all quantum fields violate these point-wise conditions because they require that at every point, these quantities are non-negative. So the first task is to have singularity theorems with weaker energy conditions. So the conditions that I'm interested in this talk are kind of smeared conditions. So we have the quantities appearing on the classical energy conditions, but now they're smeared over geodesics. So we have some test function f, and then we are averaging over portions of a null or time-like geodesics. And then we don't require that this is everywhere non-negative, but it's larger than some negative bound that I will show what that could be. So first, we want to prove singularity theorems with conditions of that form. But these are not yet semi-classical singularity theorems. In order to have semi-classical singularity theorems, we need to also show that quantum fields obey conditions of that form. So it's kind of a two-step process to have singularity theorems with weaker conditions and to show that we actually have quantum fields that obey those conditions. So first, I will show you a singularity theorem with such a weakened energy condition that we proved with Chris Fuster a couple of years ago. So here is the energy condition we had there. So first of all, I should point out that in singularity theorems, we have the geometric form of the energy condition. So this is always a condition on the Ricci tensor. So here's a time-like version of the theorem. We have also a very similar version for null geodesics. So the Ricci is contracted with two time-like vectors. And as I showed you before, it's smeared over a time-like geodesic with a smearing function f. Now let's take a look at the bound. So the bound here has two terms, and there's the L2 norm of the smearing function f and the mth derivative, the L2 norm of the mth derivative of the function f. So here m is not specified, it's just some positive integer. And we have two constants, which are also not specified here. They're non-negative constants, qm and q naught. In addition to that very weak energy condition, we have one more condition. So this is either that the strong energy condition is obeyed for a short time. So after our the hypersurface that we measure the initial contraction, or the strong energy condition is violated before we measure that. So that might seem a little counterintuitive that we require the strong energy condition to violate, but our main energy condition is average. So if we allow some negative energy before, then that allows for more negative energy after. So either of these two conditions can hold. And then we have the initial condition. So in the original classical theory, we just had that the initial contraction K was negative. Here we need something stronger. So we need K, the initial contraction, to be less than a function of four parameters. The two are the ones that appear in the energy condition Qm and Q0. The tau naught is the time of the strong energy condition obeyed or violated, and tau is the maximum proper time of appearance of the singularity. So it's not exactly that we know where the singularity is, but we know that it is before that proper time. The causality condition is the same, it's the existence of a Cauchy surface, and the theorem works very similar with the classical singularity theorems, working with a contradiction and concluding that the space-time is geodesically incomplete. And as I said, we have a version of that theorem that is very similar for null geodesics. So we do have the theorem with weekend energy conditions. Yes.
Can I just interrupt just briefly? I just wanted to understand. Yes. So these conditions on F, because you said that M is not specified, right? So if you had, very high, large derivatives of F that are possible, then is there some reason why I would imagine that this is actually a bound which is a finite lower bound, or can it just be arbitrarily high, that lower bound? I'm just curious.
So so this bound, first of all, is not proven, right? So here we assume this bound to prove the singularity theorem, right? So I have not proven this bound. Yeah, right. Second, the F can be chosen. So it is our, we have the freedom to choose the F. So we could pick an F that this bound is minus infinity, and this bound is still, this bound could not be very useful. But if we prove an F that is, for example, M differentiable at least and compactly supported, then we get a finite bound. So we have the freedom to pick F.
Okay, so the compact support will allow you to have a finite bound then. Okay.
Exactly.
Okay, thanks.
So this is not a semiclassical singularity theorem yet. This is just a theorem with a weekend energy condition. So what do we need to go to a semiclassical singularity theorem? So the first thing is to prove what we call quantum energy inequalities for time-like and null geodesics. So here's an example of one of the first quantum inequalities, the bound on the energy density in Minkowski spacetime. So see here we have quantum fields. So we have the quantities appearing on the classical energy condition, but now they're renormalized and we take the expectation value at some state omega. And then they are smeared over a time-like geodesic. And the bound, you see, it's very similar with the form of bound that I showed you before. That was the reason that we assumed that bound. So it's the LT norm of the second derivative of the smearing function F. And this was one of the first quantum energy inequalities that was proven. The second thing we need to do is to use the semiclassical Einstein equation.
Yes. So the first bound doesn't depend on the state omega. In the first bound, if I change the state,
yes. So this is a Minkowski spacetime, and the bound does not depend on the state.
Oh, I see. Thanks.
It's state independent.
Okay.
So the quantum inequalities are bound on the renormalized contractions of the stress energy tensor. But for the singularity theorems, we need a geometric condition. We need a condition on the Ricci. So to do that, we use the semiclassical Einstein equation that connects the normalized stress energy tensor with the classical curvature. And the third step is to actually estimate the required initial contraction. So for the weekend theorem that I showed you, we have a stronger initial condition than the original theorems. So we need to do some estimates of the initial contraction to see if they're physically relevant or if the requirement is too strong for physical spacetimes. So let's get on with these three tasks. First, for time-like geodesics. So for time like geodesics, we have what we call the quantum strong energy inequality. And it is a difference quantum inequality. So what does that mean is we have the quantity of interest rho, take the expectation value, the state of interest, and we subtract from the reference state. So here we use a class of states called Hadamard states that have a known singularity structure, and they all have the same singularity structure. So when we subtract these two quantities, we get something that is finite. So subtracting the expectation value of for two states. And then we have the bound. And here the bound can actually in general depend both on the state of interest and the reference state. So this is the kind of inequality that we proved for the minimally coupled quantum scalar field. And the quantity that we have here is the quantity that appears in the strong energy condition. Because we want to use it for a singularity theorem, as I'm going to show you. So on the left-hand side, we have the difference between the state of interest and the reference state. And now the bound has these two terms. The first term depends on the reference state. And this W0 is a two-point function of the reference state. So it has been shown that this integral, the first integral, converges. So this is a finite term, which is good, but it still depends on the reference state. The second term depends on m squared, which is the mass of the field, n is the number of space-time dimensions, and this is the weak square of the state of interest. So the second term is actually state dependent. It depends on the state of interest. So this is the bound that we have proven for the minimally coupled quantum scalar field. Now, a big problem with this.
Can I ask a small question? Yeah. So are you assuming the scalar field is massive in this case? I mean the.
Yeah, the scalar field is massive.
Okay.
Yes.
Okay. Thanks.
The main problem with this bound is that we can't, in general, find closed form expression for two-point functions of reference state curved space-times. So we have the reference state here, but we don't know what it is. And if we want to prove something general, what reference state are we picking in curved space-times? So the idea that we use is that for if we have test function of small support, because we're using Hadamard states, if we take sufficiently small support, the bound still holds if the W0 is a two-point function of the Minkowski vacuum. So we're taking very small support of our functions, and we can tell that the W0 is the Minkowski vacuum. So with that small support function, and for technical assumption of having even space-time dimensions, we can put the W0 as the two-point function of the Minkowski vacuum and prove the following bound. So here, the first term now is just the L2 norm of the nth derivative of f. And here we do two things. We use the semi-classical Einstein equation to connect this quantum object, which is the expectation value of the quantity that appears in the strong energy condition, to the Ricci. So this is the form that we need for the singularity theorem. The second assumption is to get rid of the state-dependent part of the inequality. So we assume that there is a class of states where the weak square is less than some value phi max. So it's just that it's finite and less than this quantity. So with these two assumptions, we have a bound that you can sort of see that it looks in the form that we want already. But the point here is that the F has very small support. To apply to a singularity theorem, we need something that has large support. We want to apply it to a large part of a time like geodesic. So to do that, we break the geodesic into n pieces, each of some support t, and then sum the resulting inequalities. So first thought is to break the geodesic into equal pieces. But this didn't work. We want to apply that in a cosmological scenario where the curvature can get maybe very large in the past. So instead of doing equal pieces of the geodesic, we break the geodesic into unequal pieces. So this is the functions that we used. So today they have a larger support than in the past. So going back in the past, we can think of a cosmological scenario, for example. The support of each function gets smaller and smaller. And so that allows for larger curvature in the path of our universe. So with this assumption, after we sum the inequalities, we can bound the term of the sum of the inequalities, which is now going to be f with the phi n with our functions that have the small support. And we just showed that this is a sum of L2 norms of f and its derivatives, which is exactly the form that we need for the singularity theorems. So a sum of just these L2 norms. And so we have our singularity theorem. So we have the energy condition, which is in the form of the theorem with the weaker condition that I showed you before. But now we know exactly where the constants are and what do they depend on. So the Qm depends on this is just the area of a sphere, so it depends on the m, and the Q naught depends on things that have to do with the field. So the mass of the field, the phi max. We also, as I said earlier, we assume, yes.
Hello, Eleni. You have 5 minutes to go. Yeah.
Okay. All right. So I might skip some parts, but let me finish that. So the initial extrinsic curvature, as I said, it's a stronger condition than the Hawking theorem. So it is less than a function that depends on these things that we have here: the m, the phi max, the t naught, tau naught, and the tau. And the third one is that there exists a Cauchy surface, and the space-time is time-like geodesically incomplete. So let me conclude the part for the time-like geodesic with a cosmological application. So what we did is we used the lambda CDM model and data from the Planck. So important thing to note here is that the strong energy condition is violated in our universe today due to the presence of the dark energy. So we have to go in the past of our universe where the strong energy condition is last satisfied. So the Hubble parameter at that time is going to be what we will compare with the required initial contraction. So we have these 5 parameters: the mass of the field, the maximum magnitude of the scalar field, the curvature scale today, and the time scale of the singularity, and the time scale that the strong energy condition is assumed. So we used 3 different particles, elementary particles, to do the comparison. And the goal here is to minimize the T naught, to minimize the curvature. And so we see that we can have very low curvature and a tau that is actually a little larger than the age of the universe. The tau naught is not very important, actually, what we found. And so we can take it as half the T naught. And so we see that at least for 2 of the particles that we looked at, the pion and the proton, the required initial contraction is actually less than the observed one. For the Higgs, due to the large mass of the particle, it is larger. And so we cannot prove a singularity theorem for the Higgs here, but we did prove it for the pion and the proton. I want to talk a little bit about null geodesics in the last few minutes. So we do have a quantum inequality for the null energy density. Here the L is a null vector, but this is averaged over a time-like geodesic. So the question is, can we have the same over a null geodesic? So something similar that we had for the time-like ones. The answer is unfortunately no, because there's a counter example to bounds like that. Fuster-Roman considered a particular example of a state where the lower bound became more and more negative. So this bound on the right-hand side would be minus infinity. So we cannot have a quantum inequality that it is of that form. So here is one idea that in quantum field theory, there is an ultraviolet cutoff, which restricts the three momenta of the states in the example that I showed you. And so it was proposed that we have the smear null energy condition, which includes a UV cutoff. So what do we know about this bound? First of all, this constant B is not measured, but we can think that it's probably some number much less than 1 for a lot of semiclassical QFTs. So it's not saturated because this inequality is not saturated in control constructions. I should mention here that the capital N is the number of quantum fields that we have. So this inequality is valid for not more than 1 quantum fields. What do we know about this bound is that it satisfies the Fischer-Rama counterexample, and there is a proof for Minkowski space. We cannot so far generalize this bound for Kerr spacetime for interacting fields, and one big disadvantage is that it actually diverges in the at the limit that the UV cutoff goes to 0. A newer idea is that maybe we can smear over both null directions. And in that case, we have a finite bound, and this is something that we proved in recent work. The advantages of this bound is that it can be generalized to Kerr spacetime. We actually have that in our paper, how we can generalize it. And the smearing is now in the other direction, and so it can be controlled, and it does not depend on the theorem. However, we cannot use directly this bound for singularity theorems because the smearing is in two dimensions, so it is over some world seat and not a world line as we need for a singularity theorem. But it would be nice if we're able to use that in a singularity theorem in the future. So just to pretty much conclude here, because I don't have a lot of time, we have used the smear null energy condition as the energy condition of in a singularity theorem, because it is exactly of the form of the weekend conditions that I showed you before. And here, using the SNEC, which is a bound, of course, only on Minkowski space here, is the M is equal to 1. The Q1 depends on this constant B, and the Q0 is 0. But it is exactly of the form that we needed for the singularity theorem. So we're using the smear null energy condition. We also have a singularity theorem for null geodesic incompleteness. The disadvantage here, the main disadvantage, is that this is a flat spacetime bound. So because I don't have time, I'm going to skip the last example and jump to the conclusions. So for time-like geodesics, I proved a semiclassical singularity theorem that it is true for coupled massive scalar field, for the quantum minimally coupled scalar field. There we estimated the curvature using a partition of unity, using this breaking of geodesic in pieces. Future work would be to calculate the curvature using a not difference quantum inequality, so not have that reference state, but actually only subtract the geometric singular part of the quantum quantity that we have. For the null geodesics, I showed you the smeared null energy condition, which is a null quantum inequality, and this condition can be used to prove a singularity theorem. In our paper, we also have an application of that with evaporating black holes. What I would like to do, and it's a work in progress, is to use the double smeared null energy condition in a singularity theorem. And I showed you the cosmological example, not the evaporating black hole, but they do support the idea, both examples support the idea that singularities are actually predicted semi-classically, and we cannot avoid the singularity at that level. We possibly need to go to a quantum gravity level to avoid singularities. And I'm going to stop here. Thank you.
Okay, thank you, Eleni, for this nice talk. So now this is open for questions. So, okay, Sriram. Yeah.
Hi, Eleni. Thank you for a wonderful talk. My question is, what are the kind of states, for instance, if you're in flat space-time, that saturate the bounds, inequalities? Are these the squeeze states?
So we're talking about the null case, yeah?
Right.
Right. So are you interested in the states that saturate this inequality here, with the UV cutoff? Or
no, even without the cutoff that you had earlier.
Oh, I see. Yes. So these are the example that they use here is a vacuum +2 particle states. So what happened is that the three momenta of these modes get large, and as they get more and more null, you can imagine. And as that happens, the bound on the right-hand side becomes very, very large and negative. So it goes to -infinity. So these are the kinds of states that they consider. This is not necessarily the only states that make the bound at -infinity, but of course we only need one example of state for that to not hold.
Okay, so often, if I recall an older paper by probably Ford, do they also induce large fluctuations that is, if I calculate fluctuations in t mu nu and compare with the average value, will they become large in these states as well? Is there a correlation?
That is a good question. I don't think they looked at the fluctuation in this case. Of course, there's always a consideration here in when we're doing that. I believe that the fluctuations of the stress tensor are under control here, but that's a kind of a guess. I don't think they looked at that.
Okay, thank you.
Okay, maybe Alok.
Yeah. Hi. So yeah, one question I had was the phi max that you defined. I mean, for a quantum field, maybe I missed it. I mean, what is the computation for phi max?
Yes, you didn't miss it. I didn't show it because I wanted to do an overview. Yeah, that's a good question. So we actually, what we did is we considered KMS states, and we calculated based on some temperature, what is the weak square of those states. Okay. So we put a kind of a maximum temperature that after that we consider our model is not valid in order to calculate the phi max. So in this case, the idea is that either we get a very high temperature, like very, very early in the universe, or the phi max is under control. So that was the calculation that we did.
I see. Thanks. I need just one more small question. Sorry, that in the if you take de Sitter space-time, then even if for a sub function with a small support, I mean, if you take the Bunch-Davis vacuum, the result would be identical. I mean, insensitive to these details of Bunch-Davis versus Minkowski for function of very small support or something. Is that the statement? Or I mean, if I take some other vacuum in de Sitter, for example, not Minkowski.
Yeah, it would. We haven't tried it, but I assume it would be different because the reference state is in the bound. So I assume we would get a different bound if we use a different reference state. But this might be something good to try.
Okay, thank you so much.
Okay, maybe last question by Sumati.
Yeah, I think there's also a question by Dawood, but it's in the chat box. But I just want to quickly ask, so the use of a UV cutoff, of course, when you take this kind of UV cutoff, you violate Lorentz invariance and covariance, etc. Have you thought about other sort of more covariant ways of taking cutoffs?
So first of all, we the cutoff that we took is Lorentz invariant. So that is not a problem. So I didn't show you how to define the UV cutoff here, but it is a Lorentz invariant cutoff. So that's not an issue.
All right.
But what happens in a curved space-time?
This is only proven for Minkowski spacetime, and okay. I think this would be a problem if we have curvature. Yeah.
Okay, David Prasad, there is a question in the chat. Maybe I can read out. Daud asks, can you please elaborate on the calculation of curvature on slide 20?
Slide 20. So the calculation of curvature for here, yes, exactly. So go to the here. So this is where the issue of the reference state comes in, is that we prove this inequality by subtracting two states, the state of interest and the reference state. So this is one way of proving an inequality. The second way is what we call absolute quantum inequalities. So here, instead of subtracting the reference state, remember we have Hadamard states that have a known singularity structure. So what would we do is subtract the Hadamard parametrics. So the Hadamard parametrics includes the singularities of the Hadamard state, and it's a purely geometric quantity. So it depends on space-time properties. So it has components of the curvature. So here we would subtract just the singular part of the state that depends on the curvature, and then the bound would not now depend on a reference state, but it would depend only perhaps on the state of interest here and some curvature components. Does that answer the question?
Daud is unable to speak for microphone issues. So I presume, yes, Daud, you need to write to Eleni if you have further questions. Yeah.
Yeah, I mean, I don't see any other questions raised hand. So maybe with this, let us thank the speaker, Eleni, for her excellent talk. And with this also, let us thank both the speakers of this session, Anuradha and Eleni.